After having the understanding of basic flow patterns, we we actually need to combine them, and because of the two functions, these stream functions and velocity potential, both are satisfying Laplace equation, which is linear. We can add up these, two different two or more number of stream functions, which may give some kind of, a solution, or which may reveal, you can say, a flow pattern altogether. So, if, as you can see, it is written psi1 and psi2 are each solutions of a particular flow, then psi1 plus psi2 is also another solution because of this linear characteristics, which actually is known as superposition. So these two can be, or two or more can be superimposed, so that the combined stream function is another stream function altogether. So in this part of our discussion, if you have gone through all the combination of basic flow patterns, somebody is asking entry, okay, they did. So if you have gone through the different flow patterns which are being added, starting from uniform flows and source flow, then source sink, dipole, or then combination of this uniform flow and source sink pair, then combination of uniform flow and dipole. To the end, we actually combine three different patterns, uniform flow, then dipole, along with the irrotational vortex. So that is the last exercise that we did, and from that we identified a particular phenomena. Basically, this is a kinematics. The entire treatment of potential flow is the kinematic treatment, but if you have seen, towards the end, we have tried to look into the dynamic perspective of the flow pattern, and thereby the
Sir, someone is trying to join, sir.
But in my screen it is not showing. Devjit was trying to join, I admitted him, but right now I don't have any notification on my screen.
Sir, Devjiti bolchilo.
How to ঢুকিয়ে দিচ্ছি ওকে, ঢুকে গেছো? Devjit, are you there? I think you are. Devjit আসো তো, নাকি আবার বেরিয়ে চলে গেছে? তো আসলে দেবজিৎ কি আমার সেকশনে, ড্রয়িং সেকশনের ছেলেটা না? দেবজিৎ দাস, এটুর আর কেউ আছে? এনিওয়ে, তো ও সম্ভবত বাড়ির দিকটা ওইদিকে, ওর প্রবলেম আছে নেটওয়ার্ক। এনিওয়ে, তোমরা যদি অন্য কেউ পারো ঢুকিয়ে দিতে পারো, কোনো অসুবিধা নেই। জানি না ঢোকাতে পারে কিনা।
না স্যার, আমরা পারবো না, হোস্ট নই আমরা।
না, কিন্তু এই অনির্বাণ, তো তুমি ঢুকলে কি করে? তুমি,
আমি ওই ইনভিটেশন, এটা তো
ইমেল ইনভিটেশনে তো এলাও করতে লাগে না।
হ্যাঁ
হ্যাঁ, ওটা ইয়েস
করতে লাগে না। হ্যাঁ, সেটাই তো।
না, অ্যাকচুয়ালি ইনভিটেশনটা যদি ইয়েস কেউ করে রাখে তাহলে লাগে না। ম্যাক্সিমাম ইয়েস মানে করে রাখে, কিন্তু দু একজন ওটা না করলে তখন পারমিশন লাগে, মানে
আচ্ছা
ওই একটা রিকোয়েস্ট আসে। ওটা ইয়েস করা থাকলে পারপিচুয়ালি যে কোনো সময় ঢুকে পড়তে পারবে। তো যারা জানে না একটু বাকিদের বলে দিও। তো এনিওয়ে, so a combination pattern, basically the main objective, if you have gone through all these combinations, you will find there is a similarity. What is that? The main thing is that after combination, we obtained a combined string function, and then we have tried to find out a point that is known as the stagnation point. What is stagnation point? I think we have learned
ফ্লো ইন পাইপে পড়েছে।
Sir, where flow velocity becomes
Yes, sir.
zero.
হ্যাঁ হ্যাঁ
where flow velocity becomes zero. So that is what you want to say as the stagnation point. Yes. Actually, if in terms of head also, I mean, we have the stagnation head. That means if in a flow field, if at a particular point, if the flow velocity can be brought it to zero, so that point, so that at that particular point we have the static head and the dynamic head converted into a head, total head, that is known as stagnation head, and that respective point is known as stagnation point. So the important thing is that at stagnation point the velocity of flow should be zero. So here we actually in all the combination, the treatment was first to obtain the stagnation point. What is the reason? Because that have you understood the reason why in all the combined flow pattern? So now, as you can see in your screen, is coming the first one, uniform flow and source flow, the combination.
স্ট্যাগনেশন পয়েন্টে প্রেসারটা ম্যাক্সিমাম হবে, তাহলে মানে ডিজাইন পার্সপেক্টিভে ওই জায়গায় মানে ফোর্সটা বেশি লাগবে, ওই জন্য হতে হবে।
Any other opinion? Design perspective থেকে we have tried to say okay. That's a good attempt to answer this. Any other opinion? আর কারোর কিছু মনে হয়েছে যে কেন প্রত্যেকবারই আমরা আগে স্ট্যাগনেশন পয়েন্ট বার করছি, and then we have done another thing again for all the cases. After getting the stagnation point, আমরা কি করেছি? We have tried to find out the value of the stream function at the stagnation point, isn't it? So what is the value of the stream respective to stream function at the stagnation point of that particular combination of flow that we have tried to obtain? And then we attributed that to the equation of the stream function or the expression of the stream function, and that we denoted as the equation of streamline passing through the stagnation point. Okay, so and that actually gives a very important aspect of this potential flow. Although this addition of the two functions, or the two functions are, I mean, as I have said in the earlier meeting, that these functions evolved from the mathematical perspective. But after this addition, and thereby after getting the stagnation point and the streamline passing to the stagnation point, actually one can have some idea of a shape of a body which if it is placed on a free stream velocity that is u0, what will be the resultant streamlines passing over the body? And if the body is not penetrable, or you can say rigid body, so flow past a particular body shape, this we can have from these combinations. All right. So that is one major importance of finding out the stagnation point followed by the streamline, equation of the streamline passing through the stagnation point. So that particular streamline, the contour that it actually represents, if you solve that particular streamline for different point in the flow field, you can get a curve or a contour. So that contour can be thought of as a demarcation between two distinct flow. Okay, and one which is common for all the cases is the uniform flow or the free, or what we can say the free stream. So as if that particular demarcation of the boundary can be thought of as the surface of a body, and that can be thought of as the shape of the body perhaps. So what will be the streamlines passing over that body for an ideal flow situation, of course. That information we can obtain by this combination of the basic patterns. So later actually, when the design that you were talking about, while designing the shape of a body, this gives us the primary idea about what should be the shape of a body so that it gives better efficiency, or so that the flow remains attached with the body itself. So it is always our objective remains more or less this same for getting a shape, and when that particular shape, I mean basically I'm talking about any kind of vehicle, be it aerial or underwater, whatever. So to have an efficient, I mean, from fuel consumption point of view, always if you can able to have the flow particles adhering with the body surface, there should not be any kind of separation of flow from the body, then the energy loss can be minimized. Okay, we will see in our boundary layer flow how this separation takes place and how to minimize that. So if the shape could be something like this one in your screen, this red highlighted one, actually that is what we call as a half body. That means it is having a nose which is converged to the point S, and but the trailing edge of this particular body is extended to infinity. It is two asymptotes are there, and this streamline, this red one is the streamline that we obtain, which satisfies the stagnation point. Okay, and the value of that particular stream function is m by 2 plus minus m by 2. So there are actually two asymptotes, and if you solve this particular stream, so it is actually approaching those asymptotes towards infinity. So that gives us the demarcation, as I said, between two distinct flow. One is the uniform flow that is leftwards of this particular streamline, and inside the streamline, this streamline, I mean all other lines are also streamlines. So this particular streamline, inside which we are having the source flow prevailing. But of course, it is not exactly the source flow. The effect of uniform flow still inside the body is there. But I mean, we are more focused. We are going to focus more on the outside of this streamline, as I said, to have a particular knowledge of a body shape, and if it is subjected to uniform flow, what will be the resultant streamlines passing over the body. So this knowledge we get from a purely mathematical exercise. That is why In all the other cases also, you can see that we had. I'm not going into this detail. I mean, do you require any kind of further discussion on this exercise? Because these are, I mean, in the video lectures, these are
No, sir. No, sir.
detailed. I think,
Sir,
yes.
sir, I have a doubt in the sign convention of source and sink, sir. Sir, here you have given VR equal to minus 1 by R, d psi by d theta. But in the SK book or SK book or any other book, the sign convention.
আগের দিন এটা নিয়ে বললেন
You please just see the recording of the yesterday's meet. I have given a caution on this particular sign convention issue.
Okay, sir. Okay, sir.
I think yes, that is true. You will find this sign completely opposite in some text, but it is not wrong. But you have to maintain the consistency. That is what I mentioned yesterday, and still I repeat that. So if you have doubt, you can just go through that lecture.
Okay, sir.
So I'm not going into these details. I think these are already covered. So the point was, I mean, here we had this m by 2 as the resultant value of this stream function at theta equals to pi. So, and as I was saying, basically the composite flow consists of flow over a plane half body. Half body means this the nose like shape that you have seen. So this is basically the half body. As if you can correlate this with the front end of aerodynamic body. Typically, if you have seen an aircraft, the front end is typically having this kind of a shape, or a high-speed train. If you have seen, those are also like this kind of a shape. So genesis of having this type of a shape actually came from this potential flow analysis. Because, as I said at the very beginning, that the evolution of this potential flow is much earlier than the hydrodynamic study based on experiment and the boundary layer flow, which later came. Okay, so this is one of the significant finding, you can say, which gives some kind of clue to the engineer designers to design a shape that will give a more efficient, shape for the moving vehicles, different types of moving vehicles, to give more efficient in terms of fuel consumption, in terms of its performance. Okay, so once we get this combined stream function, the respective velocities are being obtained. And here, another interesting part is that, I think this also has been repeated. If you can see the expression here, 23A I'm referring to, here you can see that this is a combination of two stream functions. One is written in Cartesian reference frame and the other is in polar coordinate frame. Okay, as such, this combination we use frequently in this particular section of flow and potential flow analysis. However, why in the next step you can see it is being replaced by or expressed in terms of the polar coordinate form, that is r sine theta. Okay, so sometimes, and frequently actually this swapping, you may have seen that this has been taking place. Sometimes the treatment was based on the polar coordinate frame, sometimes it was based on the Cartesian coordinate frame. But whatever frame it is basically for the convenience of handling the equations, which actually should result the same kind of pattern. The way one can able to handle it accordingly, he or she can use the coordinate frame. Okay, So after having this kinematic description, then the pressure at any point in the flow field can also be obtained by simply using that governing equation at the very beginning we have seen, that is nothing but the Bernoulli equation. So using that, taking one point as far away from the combination where it is being very significantly prevalent, that means far away from that area, where you are having only the uniform flow to prevalent, then that is you have this U naught only as the description of the flow field, and there the pressure is the ambient pressure, or that pressure is denoted as P naught, which is pressure at infinity when V is equal to U naught. So this is the mathematical statement. I mean, at infinity, there should not be any kind of effect of this combination on the this uniform flow. Okay, so it is basically some distance away where the effect is negligible in a finite scale. So there we have this one as the total energy, and that should be equated with the 1 at any point in the flow field where you have the combination effect significant. So V is the velocity at any point on the flow field, and at that particular point, if you consider the pressure to be P, you can able to find out the unknown pressure knowing this this U and V. I mean, this V and this V are different. I mean, one is the capital V, another this one is the small v, that is the Y component. So this is the basic way by which we can find out the unknown pressure P. But the condition is that you should able to know this the two components U and V. So after that, some dimensions of the half body, just some dimensions, just some basic or some very prominent dimensions we have tried to obtain. One is this particular distance from the origin of the source, or this actually is the origin of your our partition frame of reference as well. So this dimension actually RS you can obtain by using again that particular equation of the stream line passing through stagnation point, because this is our stagnation point, and that will actually gives us this distance RS earlier. So, and these two intersections, if you are able to find out, these actually this portion more or less the two extreme dimensions you can obtain. So this part is defined as, I mean, this one is defined as y max plus minus. Okay, so and that actually can be obtained by this exercise, you can see. Then we moved into source sink pair, and that gives us a kind of profile like this, whatever you can see. So it is the same exercise, you can see. Again, the thing is that, as I said, there are very frequent transfer from one coordinate frame to another. We have to live with it while doing this potential flow analysis. Okay, and another particular aspect, notable aspect, you can say, typical for the way we have treated this potential flow analysis is that in entire combination we have only dealt with the stream function. We have not dealt with any kind of velocity potential. It is not that velocity potentials cannot be dealt with this combination flow pattern. I mean, one can also continue to find out the combined velocity potential as well. We have left it out, but you can try with getting the expression of velocity potential. So the way actually this pressure evaluation after these two combinations, source sensing and dipole, that means again this dipole or doublet is another mathematical concept from the very statement of this dipole, if you have observed. That is, you are actually bringing these two points, the source and the sink, the origin of the source and the sink, close to each other. I mean, close means indefinitely close to each other, so that the distance A tends to 0. But the product strength M and twice A, basically source and sink are separated by the distance twice A. But the product is finite and constant. So that means as you are bringing in these two flow patterns, source and sink, so that virtually they are going to merge with one another. Simultaneously, if you want to maintain this product as finite and constant, means basically you need to increase the strength M, isn't it? So you are reducing A, means it is just a trade-off between A and M. As you are decreasing M, if you are making A tends to 0, you need to make M tends to infinity. So it should be very high strength M, so that you can have this product to remain live in the expression. Basically, that is the main objective, and that twice AM later we denoted as D, which is denoted as the strength of the doublet. So you get the expression of this psi as D sine theta over 2 pi r. Okay, so then we have moved into the combination of uniform flow, source and sink pair. Okay, so this is a source sink pair that we have seen earlier. The moment you combine it with the uniform flow, the resultant family of streamlines gives this type of an flow pattern. And here we have again obtained the stagnation point, which incidentally we are having now two stagnation points instead of S. For a half body here, as you can see, we are having S1 and S2 as the two stagnation points, and which are actually symmetrically placed, and both are placed on the axis, x-axis. So this is 1 and this is 2, S1 and S2, and this actually gives us the streamline passing through both S1 and S2. There is the stream value of the stream function we obtained, and then the equation that results to another contour, which looks like a complete body. The trailing end is also converged here at point S2. So this body we call as a oval separate body, but please be assured that there is no body here. It is a complete mathematical description. But as if we can conceptualize the existence of a body like this, inside which some kind of flow patterns are being seen, outside which a different type of flow pattern can be obtained, okay, or can be seen, so that we can think about existence of as if a solid body, as we have conceptualized for the half body. So this is known as Rankine oval. Okay, and as if the streamlines, if this kind of a separate body is placed in an uniform flow of u naught velocity, and then the flow or the streamlines will adjust themselves like the one you can see here to negotiate the presence of the body. Okay, so this is basically the finding from the mathematical exercise, we can say, for the source and sink pair. Then we moved into this combination process for again, I mean, the size of this Rankine oval we have tried to find out. One important aspect, or you can say the difference between this size of Rankine oval and that of the half body, is that to find out this y max, that is this dimension, I'm talking about. So this is actually the Y max, this OM basically. This is your Y max, which the expression of which you can see obtained here, and that actually contains, I mean, W is 2Y max, total weight will be 2Y max. So this is an equation where you have a variable which exists on both sides. So Y max at the left hand side, Y max at the right hand side, or in terms of OM, if you look, this OM is here as well as Y max. Y max and OM both are same. So how to solve that? I mean, numerical techniques you may use to solve so that you get the Y max value. Or else, if you want to do it by analytical means, this is what we call as trial and error method. So you need to start with a particular value and see whether it is satisfying the equation or not, and then you change it. Like in some problems, I think in your friction factor using Moody's diagram, some problems require that particular technique of trial and error. Anyway, so then from source and sink pair, the second, the doublet actually is being added with the same free stream or uniform flow. That resulted this particular streamline as a perfect circle, and that can be thought of as flow past a cylinder. So that is the importance, you can say, of having the concept of a doublet or dipole flow, or the mathematical expression of this stream function for that particular type of flow situation. Ultimately, we get an idea of the streamlines, how they may negotiate this a body which is a cylinder, and we are looking one side of the cylinder as if, I mean, and the axis of the cylinder is perpendicular to the screen. Okay, so that view is basically a circle. So the streamlines passing over the circle is the stream, is maybe the streamlines for an ideal flow. If the flow is ideal and it is passing over a cylinder, typically the arrangement of the streamlines may be like this. And here we again came back to find out the pressure distribution. Now this gives us another important, very important revelation. Once you have the pressure distribution obtained, and from that, if you have a distribution of pressure over a surface, if you integrate that particular pressure over the entire surface area, you get the resultant force acting due to pressure on that particular surface. So that exercise we have done. Before integrating, actually, look, if you look into the pressure distribution at psi equals to 0. What is psi equals to 0? Psi equals to 0 is basically that value of stream function passing through the two stagnation points, or it is actually the equation of the streamline passing through the two stagnation points. That is actually the circular one, or in other words, from the conceptual point of view, that is the, you can say, the surface of the cylinder actually. Okay. So the entire treatment of finding out the pressure distribution is on that particular streamline, where we are having the value of small r taken as capital R. So capital R is basically the size of the body. If it is a circular body, per unit length only, you can say the body is well defined. Of course, the length part or the height, whatever you say, is not being defined here. But it is the radius that only counts for defining a circle, and a circle is a view of a cylinder, one view of a cylinder. So in that sense, actually, the pressure on the cylinder at R equals to capital R has been obtained, and then we got a coefficient, basically, that is a non-dimensional coefficient. So in fluid mechanics, frequently we do this kind of non-dimensionalization for having a generalized feature of certain phenomena. So here also this kind of treatment has been done. So that is actually known as pressure coefficient, CP. If you look into that, that is basically the difference between the pressure on the cylinder and the pressure at infinity, that means far away from the cylinder where you have the pressure P naught. So Pc minus P naught over half rho U naught square. Half rho U naught square is also another known term to us, that is basically the dynamic pressure, isn't it? So this ratio is basically we have defined as Cp, and that gives you a form which can be plotted against theta. Theta is if you consider this to be the cylinder, then say, so this is the direction of theta. So this is the starting point 0, and full rotation gives you 2 pi. So here typically the figure has been drawn up to pi, right? And so I mean on your right hand side you can correlate with this. So this is the part. This part actually only has been shown in this variation of Cp with theta. And on the other side, it is the repetition, as you can see. So once you know this Cp, from this knowledge of Cp, one can also have the idea of the radiation of pressure over the surface, or on the mathematically on the radius r smaller equals to capital R. So from that, see here there is no magnitude of the pressure is being plotted. It is just the nature of pressure that is expected. And we can have two distinct zones. One is positive pressure zone, and that too is very symmetric about the this particular circle as I have marked. So these two zones are positive pressure zone, and it is absolutely symmetric so that they are going to nullify each other. In a similar manner, we are also having two zones of negative pressure or suction, because this is the direction of Cp is negative. This zone I'm talking about, which corresponds to this zone. Okay, so here as it is Cp is negative, means the pressure is going to be negative. That means it will be a vacuum condition on this area, and the same will be repeated exactly on the opposite side. So it's kind of a mirror imaging. So this means without going for this exercise that is being done in the very next step here, without going into that, by looking into this pressure distribution, one can straight away state that there won't be any kind of net force associated due to this flow past a cylinder. Can we say that?
Yes, sir.
And mathematically also it can be shown. So that actually corroborates your our hunch, you can say, or expectation. But in actual situation, so this actually means that whenever a cylinder is placed with its axis perpendicular to the free stream flow, which is uniform, then due to that, there won't be any kind of resultant thrust acting on the body. I mean, this is typically against the real situation. This is a contradiction with practical experience, because any separate body, be it a cylindrical or any other, whenever it is subjected to a flow field having a certain uniform velocity, always we experience a thrust. Forget about a cylindrical body. Whenever you walk and whenever you run, you can identify the difference. When we run, we get exhausted at a much faster rate than when we walk. What is the reason? The reason is simple. When basically, if you place the coordinate frame with your body, it will be the situation just like the same we are discussing. As if wind with a particular velocity, that is the velocity at which you are walking or running, is flowing past you. So that will create a kind of a force which we call as a drag force or a thrust due to that. And that force you need to overcome so that you can move at that velocity. You need to kill that particular force so that you should have a steady velocity. So that due to that, if you have more amount of velocity of yourself, that means your running speed is of course higher than our walking speed. So that actually calls for more amount of thrust that you will be experiencing. So you need to exert more energy to overcome that force. But here we see that mathematically it is showing that whenever a body is subjected to a flow situation like that, if it is an ideal flow, there won't be any kind of resultant thrust acting on that body. Such contradiction is known as D'Alembert's paradox. Later, we will be recalling this situation when we again visit our boundary layer flow and we find the answer there. What problem is there? Okay, why we are having this zero resultant thrust. So for the timing, it is our it is our observation from the mathematical treatment that the resultant thrust is zero for a body subjected to a uniform flow, which is far away from the practical experience, and that is being denoted as D'Alembert's paradox because it is attributed to Rana, to the person who first noted that by this treatment. Okay, so then we actually extended our study from adding these two, uniform and doublet, to another pattern, that is your free vortex. So we are having basically this addition. We know it is basically flow past a cylinder, and this addition actually means that the cylinder which is rotating. It is not a cylinder which remains static, rather as if you are having a rotating cylinder about its own axis. Under such situation, you see there are regarding the stagnation point, there are three possibilities. Actually two possibilities. For these are this is one set where you can have the location of the stagnation points on the radius smaller equals to capital R from two distinct points to merging to a single point S in the second figure. And if you are having this term, this gamma over 4 pi R U naught greater than 1, then basically the solution here is not possible, which indicates that your stagnation point do not remain on R equals to small r, rather it will be somewhere else, which means that you are having your stagnation point not on the body, rather it will be somewhere else beyond the body. Okay, so that is a typical figure which is shown here, and these are the other lines are the streamlines which one can expect. Okay, so then at R equals to capital R, once again, if you then do the same treatment as it is done for the case of uniform flow plus doublet, you will end up with, once again, no resultant thrust in x direction, but here you can have a resultant thrust in y direction, or in other words, you can have a Fy. Okay, and this is the expression that can be obtained after doing certain extensive mathematical treatment. Okay, so we have now the moment you add free vortex in this addition, in this combination, immediately we get one a very interesting result. That is, we do not have a drag force d, that is d equals to 0. So it remains same as it is for the previous one, but we are having a lift force, or L, that is a force in y direction, or a force normal to the direction of the flow, isn't it? So this lift force is known as this comes from a theorem which is known as Kutta-Joukowski theorem, and here this is a negative sign associated with the flow. So this indicates that, as it is written, if the flow is from left to right, one can experience the circulation. If the circulation is anti-clockwise, then the lift force will be downward. That means it will try to drop the body, the cylinder body, downwards. Okay, so this is a kind of a force which is a transverse force. So we can say it is a transverse force that is normal to the direction of flow. And this phenomenon is known as Magnus effect. I mean, later this effect has been experienced experimentally or as well. So I think this kind of a situation one can also correlate with the spinning of a ball and its the loop that it takes, that it takes after a certain distance it travels. There is a sudden drop in its altitude. If you throw a ball along with a spin, typically you can consider it like this. I mean, here if you want to say, so this is the ball. If you have thrown it in this direction, along with the rotation. Okay, typically this is the rotation about its own axis. Okay, so if it is being directed in this direction and having with a rotation, so as if you are a spinner. So this can be thought of by fixing the coordinate axis with the ball. So the situation will be something like this, where the ball is only having a rotation. Okay. And if you look from, the ball is here, and you are having this as the, so this is moving at a velocity. You have given a, say it has attained a steady velocity. So this will be the situation now, right? And if you look it from this direction, the this is the direction of rotation, right? So it is anti-clockwise, right? So here you have fixed your coordinate frame. So the previous one, on the top figure, this is the situation you have x, g, y, g, let us say, ground, actually, ground fixed coordinate frame. Here it is fixed with a body. It is x, b, y, b, let us say. So this will be the situation, and that will result the one which we have seen. So that actually, I mean, is the spinner which the loop, amount of loop that the spinner gives, there will be a sudden drop in the trajectory, and the skill by which the player does it. I mean, of course, we not know the theorem, the theorem. And also, see, here it is an ideal flow situation, but still you are having a force. But later, uh, actually, when you are having no the ideal flow, rather it will be a real flow situation, so the surface friction, etc., will be there. It is not ideally the one type of force that can be expected for a real situation. It will be rather complicated. First of all, you will be having surface friction that should be incorporated, and accordingly the flow pattern will slightly alter. The second one is that the ball that we were discussing is not a cylinder, rather it's a spherical object. So it should be a kind of a three-dimensional treatment which is required. But still, I think most of us have seen this type of phenomena, either for a cricket ball or a tennis ball, whatever. So the spin along with a direction of its movement as a combination will result a transverse force. I think all of us have seen that, and also in case of a football trajectory of a ball, when a free kick is being taken, this movement of the ball is due to some kind of transverse force. Otherwise, it should move straight, absolute straight. But again, I mean, one should not have the entire analysis correlated with this treatment. This is an ideal flow treatment. But this gives some kind of sense that this type of transverse force will be there. And later, by experiment, different experiments, as well as having the boundary layer flow theorem, this particular trajectory motion are well explained. Okay, so this is about the potential flow, and you can have
Sir?
some kind of yes.
স্যার তাহলে তো ওই টেনিস বলটার কোন ডিফ্লেকশন হবে তো
হয়তো যেটা একটু ডিফ্লেকশন হয়তো, যেটা টপ স্পিনের ক্ষেত্রে টিপিক্যালি দেখবে হয় গিয়ে ঝপ করে পড়ে যায়, এটাই তো তোমার বুঝতে পারে না। ঠিক আছে, তুমি কতটা জোরে ছুটছো এবং তার সাথে কতটা স্পিন দিচ্ছ, ডিপেন্ডিং অন দ্যাট উড বি আ সাডেন ড্রপ অফ ইটস অফ দ্য হাইট ফ্রম দ্য গ্রাউন্ড। মানে ওটা যেটা টিপিক্যালি ধরো একটা প্রজেক্টাইল মোশন আমরা এক্সপেক্ট করি, বা প্রজেক্টাইল মোশনটা তুমি যে ক্যালকুলেট করবে সেটা হচ্ছে জাস্ট উইদাউট এনি রোটেশন অ্যাবাউট ইজ ওন অ্যাক্সিস যদি একটা অবজেক্টকে ছোড়া হয়, কিন্তু সেই প্রজেক্টাইলটা চেঞ্জ হয়ে যাবে যদি তার তুমি একটা স্পিন ইনজেক্ট করে দাও বডিটার মধ্যে, তাহলে কিন্তু যতটা এক্সপেক্টেড ততটা না গিয়ে তার আগেই পড়ে যেতে পারে, ডিপেন্ডিং অন দ্য রোটেশন ডাইরেকশন। অন্য যদি উল্টো দিকে করো তাহলে আবার উপর দিকে উঠে যেতে পারে গ্রাউন্ড থেকে, মানে যদি ডাইরেকশনটা ঘুরে যায়, মানে তুমি যদি অ্যান্টি ক্লক হয়ে যায় ক্লক ওয়াইজ রোটেশন দাও, তাহলে বলটা যেটা ব্যাক স্পিন উপর দিকে উঠে যাবে, বুঝতে পারলো, ঘুরে পেছন দিকে চলে আসবে, উপর দিকে ঘুরে পেছন দিকে চলে আসতে পারে।
আচ্ছা
বুঝতে পারছো? তো এই ধরনের সিচুয়েশন গুলো হয়। যেমন ধরো যেটা আরেকটা দেখবে বইতেও একটা ছবি দেওয়া থাকে, যেটা ইয়ো যেটা আমরা ছোটবেলায় খেলি, তাতে দেখবে যে যখন আমরা ওটাতে বেসিক্যালি কি করি, একটা থ্রেড তোমার র্যাপ করা থাকে, যেটা রিলিজড হয়। তো রিলিজড হলে ওই চাকার মতো জিনিসটা ঘুরতে ঘুরতে উপরে ওঠে, ঠিক আছে? তো ওটা নর্মালি তাই হওয়ার কথা, মানে কিন্তু যেটা ঘটনা ঘটে সেটা হচ্ছে যে ওপর নিচ করার সাথে সাথে, ভার্টিক্যাল টু অ্যান্ড ফ্রো করার সাথে সাথে দেখবো তার একটা হরাইজন্টাল ডিফ্লেকশনও হয়। যদি খেয়াল করে থাকো, কেউ যদি ব্যবহার করে থাকো, দেন কোরিলেট, তো সেই যে হরাইজন্টাল ডিফ্লেকশনটা হচ্ছে ডিউ টু এই রোটেশনের জন্য তার একটা ট্রান্সভার্স ফোর্স তৈরি হয়। ওকে, সো রোটেশনটা অ্যাড করে এই ফোর্সটা, যে কারণে মানে আদারওয়াইজ which should have been a pure to and fro vertical movement of this wheel, দেখা যায় ওটা সামনের দিকে একটু এগিয়ে যায়। যেটা দিয়ে আমরা ছোটবেলা অনেকরকম যেটাকে বলে হচ্ছে বিভিন্ন রকম ডিসপ্লে করে থাকি, যে কায়দা আর কি করে থাকি। অ্যাকচুয়াল কারণটা হচ্ছে উই টেক হেল্প অফ দ্যাট ফেনোমেনা, অফ দ্যাট এফেক্ট হুইচ ইজ নোন এজ ম্যাগনাস এফেক্ট। ঠিক আছে, তো এইটা বিভিন্নভাবে মানে এইটার মধ্যে যেটা আছে যে যে এই পোটেনশিয়াল ফ্লো থিওরিটা, এই রেজাল্টেন্ট যে স্ট্রিম লাইন্স গুলো, সেটা অনেকের প্রশ্ন হতে পারে যেটা কিভাবে ড্র করা যায়। তো সেটা করার একটা পদ্ধতি হচ্ছে তোমরা ইউ ক্যান প্রোগ্রাম। আমি এখান থেকে বেরিয়ে যাই। ইউ ক্যান প্রোগ্রাম or else এখানে আমি যেটা দেখাই একটা তোমার এটা মানে ইউ ক্যান বিল্ড ইয়োরসেলফ দিস টাইপ অফ সিচুয়েশন। সে এখানে একটা পোটেনশিয়াল ফ্লো বিল্ডার, সেখানে ধরা যাক যেটা দেখতে পাচ্ছি তোমার স্ক্রিনটা, তো দেখতে পাচ্ছ না বলে আমার ধারণা।
No, sir.
I'm just sharing for some time. দাঁড়াও। ওকে, এবার দেখতে পাচ্ছ আমাদের একটা গ্রিড দেখা যাচ্ছে কেমন। এবার এখানে বাঁ দিকে লেফটে দেখো কতগুলো বাটন আছে। সেট স্ট্রিম মানে বেসিক্যালি দ্য মোমেন্ট ইউ টিকিট, এটা একটা বিল্ড মানে রেডিমেড একটা জাভা অ্যাপ। তো এখানে সেট স্ট্রিম করলে এখানে অ্যারো গুলো চলে এলো লাল রেড কালারের, এবং এখানে একটা উইন্ডোতে এখানে তুমি বক্সে অ্যাঙ্গেল অফ রিস্ট্রিম দেওয়া যেতে পারে। হ্যাঁ, দেন ইউ ক্যান অ্যাড সোর্স অর সিঙ্ক। তো সামওয়্যার আর এখানে ধরো একটা পয়েন্টে আমি একটা জাস্ট মাউস ক্লিক করলে একটা সার্কেল দেখতে পাচ্ছ, দ্যাট ইজ আই হ্যাভ অ্যাডেড দ্য অরিজিন অফ আ সোর্স, যেটা স্ট্রেংথ হচ্ছে 1.0। এবার এখানে মাইনাস করে দিলে পরে ওটা সিঙ্ক হয়ে যাবে। অ্যাজ উই নো দ্যাট সোর্স অ্যান্ড সিঙ্ক আর বেসিক্যালি সেম, জাস্ট ওদের তোমার সাইনটা আলাদা হয়। তো জাস্ট একটা সোর্স আর একটা যদি ইউনিফর্ম ফ্লো বা এখানে যেটাকে স্ট্রিম বলছি যদি থাকে, if you want to plot the streamline, right hand side যে বক্সগুলো আছে প্রথমটা যদি প্লট streamline যে কোনো একটা পয়েন্টে আমি যদি ক্লিক করি, তাহলে দেখো একটা ড্র হয়ে গেল একটা লাইন which is satisfying the point that I have chosen in space. So এইটা হচ্ছে আমার 2D স্পেসটা, যে 2D স্পেসের ভেতরে যে কোনো পয়েন্ট এখন যদি আমি চুজ করি, তাহলে এই যে স্ট্রিমলাইন গুলো ড্র হতে থাকছে। এটা বেসিক্যালি কি তোমাকে প্রোগ্রাম তুমি নিজেও তোমরা এটা করতে পারো। ইউ ক্যান টেক হেল্প অফ নির্মল স্যার। অলসো নির্মল স্যার এই ধরনের কাজ আগেও করিয়েছেন সেকেন্ড ইয়ারের ফ্লুইড মেকানিক্সের। ম্যাটল্যাবে প্রোগ্রাম করে ইউ ক্যান ড্র দ্য কন্ট্যুর ফর ডিফারেন্ট কম্বিনেশন। এটা মানে প্রোগ্রামটাতে তো অনেকগুলো পয়েন্ট তোমাকে একটা লুপ করে চালালে ইউ ক্যান গেট দিস কন্ট্রোল প্লট। এখানে দেখো আমি বিভিন্ন জায়গায় ক্লিক করছি, এটা ড্র হয়ে যাচ্ছে। সো টিপিক্যালি this shape now you can see it is more of the half body formationটা আমরা দেখতে পাচ্ছি। তো এই হচ্ছে ব্যাপার। এটা এখানে মানে ইউজিং দিস নলেজ ইউ ক্যান ট্রাই সাম কাইন্ড অফ প্রোগ্রামিং, writing some code to get this combination. এবং এখানে ধরো if somebody is interested to, as I said, that velocity potential or the equipotential lines we have not drawn, ধরো যে এই যে কোনো পয়েন্ট চুজ করলে you can also see the potential equipotential lines. So এই লাইনগুলো হচ্ছে আমার গ্রিন লাইনগুলো হচ্ছে equipotential lines at different points and the natures are changing. So that also you can incorporate in your code if you want to do something. তো এটা ভাবতে পারো এই ধরনের কিছু ছোট কাজ করলে you can also.
স্যার এটা কি আপনি ম্যাটল্যাব দিয়ে করেছেন?
না, এটা ম্যাটল্যাব না, এটা একটা জাভা অ্যাপ্লিকেশন। এটা অনেক পুরনো, বেসিক্যালি একটা বইয়ের সাথে একটা মাল্টিমিডিয়া এসেছিল। এই যে এখানে তোমার অনেক ভিডিও টিডিও আছে, আমরা পরে একবার দেখবো, সময় আজকে আর সময় নেই। তো বেসিক্যালি এটা হচ্ছে তোমার কাইনেমেটিক্স, ডায়নামিক্স, বিভিন্ন রকম সুন্দর অনেকগুলো ইনস্টিটিউট মিলে বানিয়েছিল। একটা বইয়ের সাথে পেয়েছিলাম। তো এটা হচ্ছে তোমার স্ট্যানফোর্ড ইউনিভার্সিটি আর ইউনিভার্সিটি অফ ক্যালিফোর্নিয়া একটা জয়েন্ট ভেঞ্চার, অনেক পুরনো, কিন্তু বাট ইট ইজ ভেরি এফেক্টিভ টু হ্যাভ দিস ডিফারেন্ট সিচুয়েশনস, এবং খুব সুন্দর সুন্দর বেশ কিছু মানে পুরোনো ঐতিহাসিক ভিডিও আছে যেগুলো আমরা দেখবো, হ্যাঁ, সময় সুযোগ পেলে। কিন্তু আমি যেটা বলতে চাইছি যে এখানে এইটা হচ্ছে এই পোটেনশিয়াল ফ্লো বিল্ডার, এটা জাভাতে চলে, কিন্তু এখন তোমার মানে ম্যাটল্যাব দিয়েও এগুলো করা যায়। সো ইউ ক্যান ট্রাই উইথ ইউর ওন if you are interested to develop a code so that giving the input you can get the patterns, and also that will help you in very, কারণ এটা মনে হতেই পারে যে এরকম একটা সার্কেল পেয়ে যাবো, স্ট্রিমলাইন হয়ে যাচ্ছে, বা স্যার বলছেন এটা আমি অনেকবারই ক্লাসে প্রশ্ন এসেছে সেটা কী করে হবে, করে দেখো নিজেরা, কিছু না পুরোটা ইকুয়েশনটা তো পেয়েই যাচ্ছি, তো ইকুয়েশনটাকে বেসিক্যালি প্লট করতে হবে ফর ডিফারেন্ট পয়েন্টস। এবার তুমি একটা 2D গ্রিড কিরকম নেবে তার উপর ডিপেন্ড করছে, এবং কতটা ক্লোজ তুমি পয়েন্টগুলোকে নিচ্ছ তার উপর ডিপেন্ড করছে তুমি ওই কার্ভটা কতটা ভালো পাবে, স্মুথ কার্ভ কতটা পাবে। তো ওই পার্টটা হচ্ছে প্রোগ্রামারের স্কিল। কিন্তু ইকুয়েশন তো এটাই থাকবে, ইকুয়েশন আর তো কিছু চেঞ্জ হবে না, হোয়াট এভার উই হ্যাভ গন থ্রু, ওই তো ইকুয়েশন, বাইরে অন্য কিছু না। ঠিক আছে, তো আজকে এই পর্যন্তই থাক। আমরা we will meet again on next Tuesday, and we can plan to have a discussion on the problems of discussing compressible flow that you have pointed out. সেইটা আমরা আগে একটুখানি ডিসকাস করে নেবো প্রথমে, তারপরে we can move into this next topic on relay flow. যদি তোমাদের নেক্সট দিন কোনো এই পোটেনশিয়াল ফ্লো রিলেটেড যদি আর কোনো কোয়ারি থাকে সেটা পয়েন্ট আউট করতে পারো, আদারওয়াইজ উই উইল মুভ ইনটু বাউন্ডারি রিলে ফ্লো স্টেট অ্যাওয়ে আফটার ক্লিয়ারিং দ্য ডাউটস অন দ্য প্রবলেমস। আর ইন দ্য মিন টাইম আমরা পোটেনশিয়াল ফ্লো প্রবলেম শিটটা সার্কুলেট করে দেবো। ওকে, তো তাহলে আজকে মিটটা শেষ করি, অলরেডি উই আর 5 minutes more we have taken. ঠিক আছে, তাহলে নেক্সট দিন দেখা হচ্ছে নেক্সট টিউসডে। ওকে,
Yes, sir. Thank you, sir.
ওকে, থ্যাংক ইউ।
Thank you, sir.
Thank you, sir.